Ladies and gentlemen, let's restart the workshop. I'm going to give a very short introduction about what we think we're going to do with complexity science at NTU. And then seven other people who are working on it will give a short introduction of what they're actually doing. But let me just to sort of synchronize talking in the language of the last talker, some of the concepts that we have heard while we talked in this group at NTU. Complexity is, I think, a key science for the coming century, and I think those that learn to master it will gain a decisive advantage over those who do not. I think that's one of the main reasons why you should do it. Complexity science seeks to identify, understand, and imply the underlying principles of complexity. Another way of saying it is that complexity science seeks to understand and master the phenomena that simple building blocks interact and form systems that can adapt themselves to changing pressures and that show an emergent behavior that cannot be predicted by studying the individual building blocks. All the grand challenges that face mankind, be it terrorism, hunger, shortage of clean water, climate, sustainability, or the impact of technology, have to deal with emerging phenomena. And as none of these emerging phenomena is monodisciplinary in nature, the scientific basis to address them must thus be developed through genuine interdisciplinary research. The complexity program at NTU intends to contribute to that scientific basis and address some of the grand challenges facing mankind in general and Singapore in particular. The program aims to become the Asian hub in the global network of scientific institutes that focus on complexity science through such interdisciplinary research. Thus, the development of interdisciplinarity will be key to the complexity program at NTU. In fact, the participants to the program who will speak after me will illustrate the broad spectrum of disciplines that are already involved in the program. But before I introduce these speakers, allow me to give a quick image of the developments of the program as we foresee it. The program has started on August 1st of this year after a lot of preparatory work by Monique van Donsel, who is sitting right in front, and Brian Arthur, who may have disappeared for a while. The long-term horizon of the program is that it will be the Asian hub that I mentioned before within a period of 3 to 4 years. And to reach that point, we will go through 3 stages, of which I will only explain the first one. And that first stage has started about 2.5 months ago. The aim for that stage are to develop an enthusiastic complexity community within NTU and a large interdisciplinary support base at NTU and outside of it. The second one is to establish visibility of the program in Singapore, Asia, and in the rest of the world. The third one is to establish an international network with similar institutes such as Santa Fe and Institut Paralimes. And the last one is to establish a sound basis from which to find external funding in the following phases. These goals for stage 1 will take about 1 to 1.5 years to achieve. And I dare honestly say that we're well underway. We have now identified about 20 talented and bright faculty members at NTU from a broad spectrum of disciplines who are presently involved in complexity research. Most of that research still takes place in, I don't want to say splendid, but anyway, relative isolation, with little interaction between the disciplines. However, that will change as this group forms the core of the complexity community at NTU that is being developed through fortnightly meetings and through fortnightly seminars. And as a result of these meetings, interest in interdisciplinary cooperation is growing within the group, as a better understanding develops about the ideas and the passions of each of the members of this community. The number of the faculty in the community is gradually expanding and now also includes a lecturer from the Singapore Management University, as well as a top scientist from NUS. Visiting scholars like Brian Arthur and Steve Lansing have already participated in the meetings, and others will in the future. The discussions so far have led to a start of crystallization, not more than that, but the start of crystallization of themes for research that could be carried out by the NTU talent in cooperation with others. And thus far, these themes that have been identified are the brain, governance, innovation, economics, and cities and resources. On the theme complexity and the brain, a brain group has been formed that works on finding interesting and relevant research questions that have not yet been addressed satisfactorily elsewhere, and through which NTU can distinguish itself. John Holland will contribute to this group on October 24th by leading a discussion about conceptual neuroscience.
I thought I was supposed to donate my brain.
Later, John, later. In terms of visibility, that's the second goal for the first stage. The workshop, this is the first workshop, is actually the first visible feed of the program. And following this workshop, the speakers of the workshop have been so kind to give another day of their time to talk with us on Saturday for the future directions of the program. Apart from this workshop, we are presently working on a conference being organized in February 2012 around the theme, More is Different. And we've heard More is Different before today. It's a famous essay by Philip Anderson that was published in Science in 1972, and that first established complexity as a science, I would say. The speakers of the conference, More is Different, are eminent scientists from all around the world. Invited guests will include talented postdocs from Singapore in the US and in Europe. The workshop, conferences, study groups, following conferences, all that will follow will create the visibility that is necessary to attract the excellent people from around the world to the program. On the international network that I mentioned, there is already the backbone of such a network with institutes like Santa Fe and IPL. That backbone was created partly by Monique and myself almost 3 years ago, and we're now in the process of putting meat to the bones. So I would say we are on track, given the fact that we're 2.5 months going. And I would be happy to tell you about all the other stages that we foresee, but I'm not going to do that. I'm going to give the word to the people that actually do the work. And there will be 7 of those. Each speaker will talk for 10 minutes. They've been instructed not to talk for more, and have a few minutes for questions. I will not introduce the speakers as elaborate as I did before. I'll just say who it is and what he's going to talk about. The first speaker is Chu Lok Yu. Is he here? He's here. And he's going to talk about organizing principles in complex systems.
Good afternoon, ladies and gentlemen. My name is Lok Yu from Division of Physics and Applied Physics. As you can see, I'm a physicist. So my research interest in this is very much affected by being a physicist, in the sense that I'd like to unravel the organizing principles and underlying mechanisms that operate within complex systems. So in today's talk, I would like to share my current work and future plan in my research in this direction. So first, let me present an example that very much motivates me. So this is the famous allometric scaling laws in biology, whereupon if we take X to be the body mass and Y the metabolic rate, I find it interesting that it seems that alpha takes a value of 3/4 empirically. So for a cat that is 100 times heavier than a mouse, the metabolic rate is approximately 30 times more for the cat than the mouse. And it is amazing that there's a variety of phenomena that scale with the body mass in the sense of a quarter power law. In fact, it is known that the heart rate, if you take Y to be the heart rate, alpha turns out to be a negative of a quarter. And if we take y to be the lifespan, alpha turns out to be a quarter. So this means that as animal size grows, pulse rate reduces, while lifespan stretches longer, conspiring in such a way that on average the total number of heartbeat is about 1 billion for every individual. So therefore the mouse just basically takes faster to reach that billion heartbeat. So the interesting thing is that what is the underlying mechanism that gives rise to this power law, the quarter power law? So there's physicist Geoffrey West, James Brown, biologist James Brown, and Brian Enquist, in fact, postulate 3 unifying principles that comprehensively explain the quarter power law, how it happens. Basically, it arises from the manner in which the body economically distribute resources by means of fractal-like branching network. So from here, we can appreciate how organizing principles can explain something as complex as a biological system. But I find that the strength of complex system is interesting because, well, it is interdisciplinary in nature. So what we learn in a biological system can be applied to complex transportation network like a city highway. So here, if we take V to be the variable for city highway or the Neocortex, while A to be the land area or the total convoluted surface area of Neocortex, you'll find that, interestingly, both systems follow the same scaling law. So this similarity in scaling law can be shown by the tables here. So if you look at the number of highways, the manner is scaled with the land area is the same as the manner, the number of neurons scaled with the neocortex surface is basically 3/4. So similar scaling behavior applies for the rest of the parameter, or the variable, between these two different systems. So this tells us, in a sense, that the two different systems may have similar organizing principles that are operating within it. Scaling laws also operates in other areas. For example, it's well known is the size of the earthquake, solar flares, or extreme situation of stock market crashes or natural disasters. And some common features in this system is the presence of what we call the critical point. And what is the underlying mechanism for this? And a possible mechanism would be what we call self-organized criticality. So I have performed some work in this area, and what we have done is that we have a way to create fractal lattices. So here you see 2 fractal lattices. In fact, they have the same fractal dimension, but they have different microscopic structure. So what we did was that we put sand particle, 1 grain at a time, into this site randomly. And when the number of sand in one site is 1, it is at a critical state. So if we drop another sand in grain, and then it happen to be on the same site, it will topple. So 2 sand topples to its nearest neighbor. And if its nearest neighbor turns out to be critical, sand drop on it, and it will topple again. So what we see is that an avalanche will induce an avalanche, and it may induce an avalanche. The interesting thing is that the length scale of this avalanche, there's no length scale in this avalanche. Okay? So the probability of this length scale, in fact, is found to scale with 2 variables, d and tau, as shown here. The d and tau there. And our work here basically generalizes this scaling law. What we found is that dw over there which is what we call the fractal dimension of a random walker on the lattice. Basically, researcher has been working on regular lattice, and that DW is found to be generally 2. But what we found is that when we have this fractal lattice, there are 2 different dimensions. DW turns out to be the time for the grain of sand to transit, to traverse within the lattice and finally dissipate out of the lattice. And the time actually scale as DW. So the result from this work shows that the microstructure of the fractal lattice actually has effects of the mean size of the avalanche. Another piece of work that we work on relates to dusty plasma. On the right, on the left here, you can see that these are patterns formed by dusty plasma. Dusty plasma basically are positive ions interacting with negative charges, and their interaction are mediated by some dust particles. And this competing interaction between repulsive forces and attractive forces between these particles actually lead to interesting patterns like clusters, voids, and in fact connected shelves. And what I find interesting is that for this same system, when I look at the one based on this that is shows an animation here, which is actually the BEC, Bose-Einstein condensate. Now this BEC basically share the same sort of interaction, repulsive and attractive and confined within some potential. The dusty plasma system also confined within that potential. So we see that this interaction led to evolution. And of course, when we look at this, we do not know what will happen. So can you predict what will come out from this system? We will wait and see. But in the meantime, let me say something about this system. Now, there is an equation known as the Ginzburg-Landau equation. There is an amplitude equation that basically describes pattern forming system. And this simulation that we are doing, basically, well, is based on a simplified version of it, which is called the Gross-Piotrowski equation. As you can see, that subsequently as it evolves, there appears things like dots here. These are basically vortices. So basically, before we even start simulating, can we foresee that vortices will appear in this? So there's the emergence property of what we call, that comes from the organizing principles within complex system. Okay, so let me continue. So this is the Ginzburg-Landau equation. So the next system I'm going to talk about is basically a socio-ecological system where we find organizing principles that happen here. Now, what happened here is that there are farmers being attracted by the better working condition in the city, want to migrate to the city, and as a result of their migration, their forests, their farmland become disused. So forests start to grow, and as a result, we can actually model this by means of 2 dynamical equations. With that, there can be 2 regimes. One is a regime where there's little migrants and also little forest growth, while the other regime is a lot of migrants and a lot of forests, which is here. So that depends on how fast the forest grows based on this model. Of course, there's another regime that is basically a composite of these 2. And the interesting thing is that there can be what we call regime shift. Depends on, well, the way in which the number of migrants actually goes from very little to a lot. This comes from the presence of hysteresis in the system. Imagine that the city becomes very attractive. So that is indicated by mu. Initially, there's very little migration. When the city becomes attractive and the farmers migrate, the system drops to this level, and you see that there is a sharp increase in the number of migrants. And when the city becomes less attractive, mean goes back. But when you go back to the same level, you realize that there's no switch because of the presence of the hysteresis. The system needs to switch even more before there's a jump back. This results from the fact that when the farmer goes back to the farm, forests have been grown. So that you need more incentive from the going back to allow him to make the decision to go back to the farmland. So there's the presence of a hysteresis in the system. This is my final slide, which basically shows my work in protein system, whereby there's also a regime shift from alpha helical structure to beta sheet structure. So this regime shift is biologically relevant. Why? Reason because now the helical structure in a good prion protein, it becomes a bad prion protein by changing to a beta sheet. So here itself, we found that it comes from a first order phase transition, and our understanding in that socio-ecological system led us to the question, would there be a hysteresis effect on this? So that is my future work, and that's all for my presentation. Thank you for your attention.
There is time for one question. We're not going to wait a minute for the question, so thank you very much.
Thank you.
So the next speaker is Chong Xiu An. I hope I pronounced it right. It's still trying to. And he's understanding the dynamics of complex systems from high frequency time series data.
Okay. Thank you for giving me a chance to talk about my work here. I do both modeling and also analyzing large volume, high frequency data. And my starting point is not actually data mining, although the methods I use have a decidedly data mining flavor. But let me just tell you where I'm coming from. So I think we've heard a lot about complex systems. They necessarily have to have these kind of ingredients, that they are composed of many strongly interacting variables, and they exhibit emergent dynamics on multiple time scales and also multiple length scales. And the text that is colored brown is actually the method that we are developing to try to tease these out from the high frequency data. And of course, the purpose of actually teasing these things out is to try to build up the hierarchy of effective descriptions. And this, of course, ties into the paradigm that more is different. So let me move on to tell you, run through 4 particular examples of my work based on these 2 methods. The first one is time series segmentation. Usually for complex systems, what you find is that the time series is not statistically stationary. It goes from one statistically stationary regime, and then suddenly jumps to another statistically stationary regime, and then maybe jumps to yet another one, and then finally jumping back and so on and so forth. And it will be interesting to find out when these kind of regime shifts happen in actual time series. And it's much more interesting to actually find out how many different regimes there are in a given time series. So in this example, we looked at the 10 US macroeconomic indicators. These are the Dow Jones US industry indices. One will be basic materials all the way up to utilities. You can use a more finer grained classification scheme that maybe consists of 30 over indices, but I think this cross section is good enough. And we then downloaded the high frequency, the tick by tick data from Thomson Reuters tick history. We processed it into half-hourly time series and then did segmentation. Because of the time constraint, I will not go through the method. So this is the results that we obtained. So EN is the oil and gas industry. You can see this. The time series is actually colored, and the color scheme is this. If it is blue, that means that for this particular period in time, the actual volatility is very, very low. Okay, if it is green, it is moderate, and if it is yellow, it is high, and if it is red, it is very, very high. So if you just compare with what economists already understand, you can associate red with market crashes, and then yellow with economic crisis, and then blue with economic growth, because generally speaking, during economic growth, the time series of different financial instruments on the stock market, they are very low. And then green can be associated, can be interpreted as market corrections. So you can see that the time scale is roughly correct based on what economists already understand. But what is more interesting is when you compare a cross-section of these kind of time series, you see that there is a temporal pattern in the segmented time series. And the oil and gas seems to have gone into a blue recovery phase earlier than, say, technology. And this is understandable because in this period of time, the US is actually recovering from the technology bubble. So people don't have any confidence in the technology sector. You have to wait till the entire economy kind of recovers before they start buying into the technology sector. And my interest, of course, is not just telling the story, but also understanding the time scale. So if we define, roughly speaking, this to be the start of the economic recovery, and this to be the end of the economic recovery, then the time scale is about 1.5 years. We've also done this similar analysis of the Japanese economy, and the time scale is comparable, but longer. It's 2 years and 3 months. Okay, so that's for recovery. Now what about economic crisis? So we then look at the period that covers the start of the subprime crisis. So it started with the consumer goods, and then followed by utilities, healthcare, industrials, and by the time the financial sector get into trouble, half of the US economy was already in trouble. Okay, and the consumer goods, we understand why it is leading the economic decline, because it is the sector that the home builders are classified into. So the green means that the volatility started growing high. Before this, it was actually blue for the non-consumer goods, and then it turned green. The volatility increased and then lowered for a period of time, and then became the volatility increased again until of course 2008, and then near October 2008 there was the Lehman Brothers collapse. So again, we look at the time scale. This is the start, and this is the end, and the time scale now is a lot shorter, just 2 months. So if policymakers who wants to actually implement policies, intervention measures, they have very, very little time to work with, compared to if they want to promote economic growth, then they have much longer time to play with. But that is in the two pictures I've shown earlier. What we did was to actually coarse grain the high frequency time series data to show a representation that's easy for us to digest visually. But we're thrown away a lot of information, for example, the high frequency information. So we can go back into the high frequency data to pull this out. So we can define cross correlations between the 10 time series. And then we can construct, let's say, because the cross correlation between the 10 indices is a 10 by 10 matrix consisting of 36 independent matrix elements. There's too much to digest if we just look at the number. So normally what we do is to show it in a graphical representation as a minimal spanning tree. So this is over the 10-year period. And then we can also focus on the crisis period, the technology bubble period, and you see that it looks like this. And then now the subprime period, it looks like this. And then what happens when we look at the growth period, it looks different. So the correlational path structure of the US economy is decidedly different when it is in the growth phase compared to a crisis phase. And then when we can do a more in-depth study, this is the subprime crisis in particular. So we can divide the subprime crisis into episodes and look at the minimal spanning tree one at a time and identify rearrangements. But most interestingly is that in September 2009, you get a minimal spanning tree that looks like this, actually persists through the Greek debt crisis of middle 2010. And this is already very close to the growth minimal spanning tree. So we believe that what we're seeing in 2009, September, is a precursor signature of economic recovery for the US economy. Of course, now I think maybe the policymakers in US do not agree. And we have also looked at Japan. Even till the late 2010, there was no signs of economic recovery. So given the time constraint, let me just skip. The time series segmentation method can be used for different kind of system because the method is very generic. We also tried looking at protein folding, but because of time constraint, let me just skip this and go on to the other method, which is also very interesting. And so I have to do quite a bit of this. And that is time series clustering. So here what we do is we look at, we try to find more detailed and useful ways to classify market crashes. So here's one caused by the collapse of the Lehman Brothers in the Singapore Stock Exchange. And if we then do a sliding window analysis of the cross correlation across the entire Singapore Stock Exchange consisting of 800 stocks, we find a visualization of the cross correlation in this manner. This correlation matrix is rearranged, reordered so that you get the maximum visual information. So here you can see that huge patch of red. The next 2-month window, you see that the correlations have died down a little bit, and it comes back up again, back up again, back up again, and then of course the crash, and then it dissipates, and becomes smaller, and eventually it returns to normal. So that's one way to visualize the information contained in the cross correlations. We developed another way to visualize it by drawing a chemical picture, so that around this period of time, the Lehman Brothers crash is around this period of time, but prior to it, there's already one giant cluster. So, in fact, if you just go back in time, you'll find that there's a series of precursor shocks identifiable from the size of the giant clusters, and then the giant clusters will break up and then fragment further and then coalesce and then eventually give rise to the market crash. So we've done this, and right now we're still in the process of going through the actual component stocks to understand what is happening from one time window to another time window. And so that's the fusion and fissions, and then this persistent giant cluster during the crash. We have also done this for the Sumatra earthquakes. So this is GPS time series data. So I'll just skip these things and show you the picture in the end. So this is the first half of 2007. We found that there are earthquakes during the fusions. And there are also earthquakes during the fissions of the giant clusters. And then there's the fusion is rapid. The fission is rather slow. And then for the pattern of earthquake is rather periodic, so we don't know whether this is due to climatic forcing or whatever the reason is. And then if you look at the later half of 2007, there's a magnitude 8.5 earthquake here, and we found that there's now a slow fusion of clusters followed by an even slower fission of the giant cluster, which correspond to a persistence of the giant cluster. So that's, and let me see what else. So we need a longer study to establish the relaxation time scale, and of course we are also using this kind of methods to understand brain dynamics, working with Professor Dusz from Poland. So that's.
There's time for one quick question. One only.
Very quick. The work by Martin Scheffer that was recently published in Nature about the telltales of tipping points,
Yes.
Actually showed that this cross correlation might give you the wrong impression of the next tipping point, and that the things that we found were more like coincidental than really meaningful, so to say. So how can you rule that out?
Oh, okay. So accidents.
Yeah.
So if you study climate change, where the time scale is immensely long, you get maybe one tipping point in every century. So that's the only data point you would have. For stock market, you see this kind of tipping points all the time. So you would be able to systematically catalog all the tipping points, all the market crashes, and then sort them into different categories. And then hopefully, with the different categories, we can understand more. So the statistical significance-wise, we will have a lot more data from financial stock markets, and also for earthquakes, because there is high-frequency GPS recording, and also high-frequency other kinds of recording, temperature, rainfall, and stuff like that, intraday. So that gives us a lot more confidence to say that what we're observing is real and not just a statistical accident.
Okay.
Yeah.
Okay, thank you very much. Our next speaker is Alexei Surin. Did I pronounce it right?
Yes, okay.
Okay. And he's going to speak about visual analytics and semantic visualization.
Good afternoon, colleagues. I'm wearing two hats here, and actually I'm replacing my colleague Wolfgang Müller-Wittig, who couldn't come from Germany. And so one of my hats has a head of NTU academic staff, and other one is deputy director to Fraunhofer IDM at NTU. This is a new research center which was officially opened only this June, and actually it existed before but under different names for about 10 years, and eventually it has become part of Fraunhofer network. And Fraunhofer network in Germany is known for applied research, industry-oriented applied research. And one of the institutes of Fraunhofer network, it is Institute for Computer Graphics Research. It has several branches in Darmstadt, Rostock, Austria, and now in Singapore as well, based, organized as NTU subsidiary. And the model of Fraunhofer assumes close connection with base universities, and we even have double degree PhD programs. And this is just how much research and application spans, and we are experts in visualization and mostly in virtual reality and real-time rendering. However, we also study human-computer interaction and various elements of visual computing. And in terms of application arena and hardware, it goes from mobile devices, then our signature device is a large touch table, then even projection walls with high definition images. And here just a few examples of what we're working on. These are both some industrial projects as well as student projects and research projects done in Fraunhofer IDM at NTU labs. And today I wanted to present just one area rapidly growing not only in the world but also in Fraunhofer computer graphics network, and this is visual analytics. Visualization of data, of course, is not a new area. It is as old as I am myself, and especially scientific visualization was very much around, and this is where we usually visualize data that has quite apparent graphical nature. And this is why one of the most frequently used application on every computer will be Microsoft Excel or numbers in iPad or Mac platforms to visualize charts, to visualize plots. But as soon as it goes to something else, then it creates challenges for first understanding data and ways how to visualize them differently. And on the other hand, we also have well-developed data mining, where we can retrieve data, but here probably the way how we retrieve data and work with this data is very much limited, if not to say one-dimensional. And somewhere in between, visual analytics comes. This is where we use advanced reasoning facilitated by interactive visual interfaces, advanced visual interfaces, and this is where we can make search of information very different from the way how we can search usually this data using standard databases. And I remember even 10 years ago, we worked on very unorthodox way of representation nuclear reactor data, and it was, well, there was some wow factor. People said, oh, interesting, we never thought that you can search information this way, but it was not well accepted. And eventually, in 10-year time, it looks like this is the time, and then we have a lot of demands for this unusual way of data interpretation, visualization, and it is not only a world trend where we combine automatic data analysis with novel visualization techniques. There are also demands growing in Singapore and in the region. And here we can give examples of market demands for interactive digital media. This is also a well-funded area. They promote this research in higher learning institutes. There are lots of requests from science and engineering because of this growing amount of data that has to be processed in more efficient way. And examples of such potential application areas are biomedical analytics, geotemporal analytics, business analytics, and probably many more application areas. And today I will just make a quick look through some recent projects done in the Fraunhofer network. And first one is visualization of and analysis of various hierarchical data, such as video segmentation, inflation analytics. It can be anything else where we use, well, more advanced than just a circular diagram visualization. And this is not what you have to prepare yourself and then visualize data. It is visualization plus some data processing tools. Second is also quite probably not very new, but establishing visual links, connections between different entities may eventually look like what you see here on the screen. And this is about companies and their shareholders, persons and their relations, documents and their citations. Come with any examples yourself. Then even today we've seen already, not this one, next slide. Here, this is about visual clustering and search in time series data. I myself did research like this, and surprisingly, we were able to find some patterns in brain activity which was not possible to find when we analyzed each individual spectrum, and only then we put them all together and displayed them with specific colors. We noticed a new pattern, and it allowed us to answer some questions which nobody even asked before. And visualization where we use, where we display multidimensional data and use for this multidimensional data colors, time, any other graphic stimuli is also used. And today we also seen in the previous talk application of this visualization where some color patterns are displayed. And yet another example. And probably in modern visual analytics, this two-dimensional visualization still dominates, because this is the way how we human mostly accustomed to work. And though we are three-dimensional, in fact, we prefer to use two-dimensional data. Probably there is also a certain threshold which we have to cross to be able to use some other interpretation. And one of the projects, which is called Visual Immersive Mathematics, gives tools and framework for high-dimensional data interpretation. Here, if you have any analytical model that eventually may result from your data analysis, this analytical data model can be then used straight ahead to visualize it, and not just by displaying shape, but it also can define a certain analytically defined color. It also can display even physical properties as well as time relationships. So we can have some moving object which is colored in some fancy way. However, these colors, they do have sense. We even can touch this data and feel yet another dimension with haptic devices. So this is just a quick overview of how visual analytics is being developed in our center, and thank you very much.
Even shorter than 5 minutes.
Good.
There gives time for more than one question.
Thank you.
In that case, I'm going to ask Joseph to come forward. And, you will have just an extra minute. And Joseph Chum is going to talk about catastrophic risk management.
Okay, this is the title of my presentation. Actually, I don't have any technical details for my presentation.
Please use the microphone.
Oh, sorry.
Oh.
Yeah. So actually, I'm not going to go through any technical details here. So I'm just going to talk about this. One of the research topics that I'm working on is about catastrophe risk modeling, monitoring, and management of complex urban systems for urban sustainability and resilience. So since 1980s, right, we can see that there's a huge increase of economic losses and loss of lives due to many different types of catastrophic events in recent years, which is exponentially increasing. They create high societal impacts. They affect the functioning effectiveness of society and businesses. My main research basically look at natural hazards, the effect of natural hazards to urban systems. such as an earthquake, which mainly I spend most time working on. Recently, I work on something to do with floods and tsunamis and typhoons. Historically, Asia has suffered the most. Okay, Asia occupies about 30% of Earth's land area. We have about 60% of world's population here, about 4 billion people. We have the largest growth of urban centers in Asia. The risk here is very high, but in general, awareness is low. So this is just some data about the number of deaths and number of victims affected by the natural disasters, and also the corresponding economic loss in US dollars due to different types of hazards. So what do you mean by catastrophe? So now, in general, when I mention catastrophe here, right, I'm referring to catastrophe due to natural hazards. Of course, the main feature is catastrophe is rare, uncertain, and leads to very severe consequences. And it will look surprising to a lot of observers who make predictions based on historical data. Now, based on some of the recent catastrophes that happened in the past 10 years, we can see that actually if we want to quantify the risk based on the historical data, right, that is not good enough. For example, look at what happens in Hurricane Katrina, which is a Category 3 storms followed by floods, okay, which leads to economic loss of about 100 billion US dollars. So those civil engineers, when they design those systems, they don't expect that those systems will lead to such big losses. This is a very big surprise. Of course, actually it's not surprising. It depends on when you look at your system, right? What is the system to you really, right? I think there's some complexity being missed out here in terms of design of systems, which I'm going to elaborate more in the future. Of course, we have Wenchuan earthquake. What happens in 2008? Magnitude 8. These areas was previously classified as a region of much lower seismicity. Of course, once again, we have a huge economic loss and a huge number of deaths. And of course, we have recent floods happening in Thailand, Cambodia, and also the earthquake-induced tsunami that leads to catastrophes in Japan. So usually when we consider design of urban systems for its sustainability and resilience, for most countries, catastrophe risk modeling and monitoring and management, right, have not been considered in a systematic way, especially for Asian countries. Of course, our main objective is to assist optimal decision-making, management strategy, or if we can, to retrofit the system. Just like if we realize there's some damage in the buildings, we try to retrofit it by repairing it or adding controllers. So the thing is, like, how do we do that, right? We need some information to do that. Of course, we have different parties of interest here, and when catastrophe happens, right, it will be interesting to understand the capability to recover and ability for these different parties of interest to handle catastrophe. So I'm going to go very briefly what I've done in the past. Basically, develop some new methodologies for catastrophe modeling and management, considering stochastic dynamics, probability theory, Bayesian theory, information theory, and decision theory. So the framework I had before is decision theoretic. We look at performance based with multiple performance objectives in terms of system reliability and failure probability. And of course, we are working in a huge stochastic dimension with thousands of random variables because of the random fields involved in the stochastic modeling. I simulate rare scenarios that can cause severe consequence. I look at lot as different levels of failure probability. Monitor system performance in terms of their reliability. But the main problem is the only thing that, at least in my field, we are only investigating civil engineering systems. So for these systems, we know what we know. We know what we don't know. And how about unknown unknowns then? Because when we try to do a prediction, right, it seems like there's some mismatch between what we model and do prediction and with the reality. So what I did before was we inspect continuum of risk levels, multiple levels of reality, look at multiple structures, layers of stochastic modeling, look at very rare scenarios, try to simulate and see what happens. But the question is, we believe that we are not doing enough by looking at isolated civil engineering systems. Because the catastrophe, right, doesn't just happen to isolated systems. It happens to the city, to the society, to a country as a whole. So my interest here is, of course, always to transform some unknown unknowns to unknown unknowns. Okay. Of course, how about unknown knowns, right? Sometimes when I talk to some researchers from in other fields, I realize that actually some of the things that actually I know, but I don't know that I know about it before I talk to some of the researchers. I don't see my own potential in it. So through communication in interdisciplinary researches, I think somehow I'm able to treat unknown knowns better. And it's very frustrating if you realize actually something you know, but you don't know that you know about it. So in face of possible catastrophes, right, of course I'm interested in urban sustainability and resilience, right, whether the system can last for a longer time for proper functioning and also the ability of recovery. Of course, when we talk about recovery, we can talk about social resilience, engineering system resilience. And we look at the catastrophe that's based on the historical data, right? It can be very at this point of understanding, but this is what creates surprises and what worries us the most. I would like to see whether these urban systems will be able to handle these catastrophes. And of course, there's some interaction with the dynamics of urbanization and climate change as well. Of course, urbanization increases humans, society structures, and infrastructures exposure to all types of risks due to natural hazards. And of course, particularly, we know that the climate change has a big effect in terms of the flood risk. And so what leads to my interest here is in complexity studies is I believe, first of all, I think some people already will agree to this, is an urban system have to be treated as a complex system. Okay. Well, it's a collection of a system of systems. I hope I'll be able to model and monitor and manage catastrophe risks. But before we do that, before we talk about manage and monitor, because the way that we monitor these type of risks, right, we basically in the past, right, the current practice is to look at isolated systems, right, without looking at the whole emerging collective behavior of the whole urban systems. Of course, we realize there's a different level of complexity. We have a multiple scale, large scale modeling. We need to understand model complex coupling interaction, okay, between different structural infrastructural network systems, building, transportation networks, like road, highway networks, mass transit railway, water supply, electrical supply networks. And the thing that we do quite a lot is the interaction between the structural, infrastructural network with the natural systems. That's usually in civil engineering, where my field is in civil engineering. Basically, we just look at the interaction that refers to. But of course, we realize that the importance, when we look at urban systems as a whole complex system, we need to realize the interaction with other types of systems, economic systems and social networks. So recently, I'm having a lot of discussion going on with Dr. Sofika Amir, the next speaker, with several other researchers as well, regarding the interaction of engineering systems and social networks. So hoping that because without understanding, right, actually we can't do a very effective monitoring and management control. Because nowadays people talk about control and management, right? They're pretty much, it depends on how you look at it. Because these unknown unknowns, right, or so-called the black swans, actually it depends on observers. To some people, they may think this is black swans, but to the other groups of people, they may feel that actually it's not, right? Something can be expected even though it's rare. So the point here is we have to identify the points of criticality at different risk levels, including those extreme rare cases. So I think that we have to use a complexity approach in order to solve this problem, okay, which nowadays I don't see we are moving anywhere. So I'm grateful to have this opportunity, okay, to get involved and interact with different researchers from different fields, and hoping that to come to with a better solutions. Okay, thank you very much.
There is time for some questions.
Yes.
I noticed that you were looking at seismic activity. I assume this is for Singapore, or is it for all of Asia?
Yeah, of course. So after I joined NTU, right, my focus will be on in Asian countries. But in the past, what I look at is because I was originally in California, so basically, okay. In the past, I look at pretty much North Americans.
Well, my question is, do you have a priority list that says the probability of seismic activity affecting, let's say, Singapore or Shanghai, with incredibly tall skyscrapers, where the bulk of the population lives, and this kind of seismic activity would cause these kinds of damage?
Okay.
Here are ways that we could mitigate them, if we knew.
Of course, this is what we are investigating right now. Okay, but we realized because we are doing some sort of stochastic modeling to get a prediction of failure probability, or the probability of unsatisfactory performance of course, for the moment it's still civil engineering systems. But we realized the sensitivity of how we structure the structures of the models. And then when we look at the tails behavior, it's very sensitive. So later on, I start to question ourselves, right? When we talk about failure probability, what is it really? I think it's just conditional one, conditional on all the hypotheses that we are making. So how we so if we say are we underestimating or are we overestimating? Okay, so I think this is my main concern right now, because when you look at different stochastic models, right, with different structures, if you look at the frequent scenarios, right, they pretty much can give similar prediction of how the likelihood of some unfavorable events to happen. But when we look at the tail, right, like something like 1 in a million, and that's something that we need to pay attention to when we look at catastrophes, those rare scenarios that cause high consequences. And it seems like we have a spectrum of answers. And I also believe that such a probability, right, actually is also evolved with time as well. So hoping that when we try to take into account the complexity of the whole of this collection of urban system, where we will come up with an answer of a higher confidence.
Okay. Thank you.
Okay, thank you.
So our next speaker is Zulfikar Amir, and he's trying to understand the complex socio-technical system.
10 minutes, right?
10 minutes, yes. And I'll warn you if it's 3 minutes.
Get my timer here. Thank you. Other than Monique, is there anybody here from humanities and social sciences? Okay. What is your field?
Management.
Management. Okay. Okay. Well, probably I'm the only speakers today here who come from social science backgrounds. I'm an assistant professor in Division of Sociology at School of Humanities and Social Sciences. My PhD actually in Science and Technology Studies, which is a social science that studies the relationship between science, technology, and society. So the courses that I teach at NTU is something related with science, technology, and society. And also for the past 2 years, I've been teaching on sociology of risk, a course that tries to understand how risk is produced in society, especially in globalized society. What I'm going to talk about today actually is part of one of my research that I've been working on with a group of engineers. Starting starting last year, I joined a group of civil engineers at NTU that is now developing what they call as underwater city in Singapore. This is funded by competitive research project from a National Research Foundation. Now, I'm just a collaborator, I'm not a PI, but I think this is very significant for sociology to contribute or to participate in an engineering project. So what I'm going to talk about here is something related with the project, although I'm not going to show you how the underwater city will look like today, but something that is more fundamental about the relationship between technology and society. And it is under this notion of technology and society that I would like to talk about the term that I use here, which is socio-technical system. Now, socio-technical system is not a new term. It's been widely used by not only social scientists, but also engineers, management, psychologists, and etc. And the notion of socio-technical system usually refers to the interactions between man and machine, in which individuals try to operate system, a mechanic system or a digital system in order to pursue or to accomplish in certain goals. Now, I would like to extend this notion actually to a broader level in which socio-technical systems are situated in a more complex environment. So the first assumption that I would like to point out here is that a socio-technical system is basically a complex system, and that's something that I would like to focus on. And it is a hybrid of social systems and technical system. Now, every artificial system, whatever the purpose it is designed to fill, is basically socio-technical system in the sense that it consists of two major elements. The first element is an array of physical and material components that what we call as technology. The computer, the building, infrastructure, everything that is physical that we call technology. That's one element of a socio-technical system. The other element is the social components that comes from a group of individuals that make up the institutions that operate the technological system. Now, in many cases, we tend to see the operations of technological system merely on the way it operates technically, and we tend to overlook how the system itself is part of a larger system of society. Because my background is sociology, I try to understand the operations of technology within society and how society itself is the operation of society itself is underpinned by technological system. So it is the interaction of social and technical system that I would like to examine, and I can see that complexity science, provides something useful for us to understand the interaction, the integrations, the hybridity of these two elements, in order for us to see, the way it operates and what kind of behaviors that it has when it comes to the situation characterized by crisis. So this is something related with what Joseph has explained. So actually, Joseph gave a nice introduction to what I'm going to talk about here. Now, when we're talking about socio-technical system, there is the goal that I would like to accomplish in my research is try to see, to what extent that a socio-technical system is resilient and how we can build a better system that has, a higher level resilience and able to withstand shocks and crises and to bounce back in the event of natural and man-made disaster. Now, it is quite paradoxical if you use complexity in science and say that socio-technical system is an emergent system where its behavior actually comes from the bottom up, and it is quite difficult to intervene into this, to arrange such a system, because it's something that is emergent. But I think there is a compromise that we can reach here, in which intervention, as I already talked to Jan today, how interventions can be part of the system, and it is these interventions that we can embed it into the system so that it's able to withstand shocks and crises. Now, before we go to that level, I think we need to at least identify what kind of components they would like to observe in order for us to better understand the characteristic and the behaviors of socio-technical system. Now, this is a very simple a diagram that shows you 3 layers of socio-technical system that I'm interested in examining in my project. As you can see here, the first layer at the bottom is technical infrastructures, which includes everything that we use in our life, from telephone lines, highways, a transportation system, power grid, telecommunication, etc. At the higher level, we can see another layer that is directly coupled with this infrastructure is the institution. Institutions is an organization that operates this technical infrastructure. We're talking about institution here includes a governmental authority, agencies, the police, and so forth, that have responsibility in maintaining or in operating the technical infrastructure. Now, institutions don't work alone. It must be supported or underpinned by what's going on in society at large. So I put another layer, which is society at the top, that also connect to the institution that operate technical infrastructure. So my interest is try to see, the kind of a network that underpin this integration of this socio-technical system. And it is these integrations of these 3 layers that I would like to locate socio-technical resilience. Now, my assumption is that if we able to model this network of interaction, at least it will give us insight how to identify key variables that is crucial in maintaining the resilience of socio-technical system. That's my 10 minutes.
Time for questions.
So how are you going to I understand the layout of what you want to do.
Yes.
How are you going to do that? I mean, is it by data inference? Is it inference? Is it by modeling? Is it by what's your approach?
Well, at this stage, I just want to try to make the conceptual framework. And I've been getting a lot of questions about what kind of data that I would like to collect, and how will I analyze it. And I think that's something that I need help from my colleague from engineering school. But basically, this is what I developed from my sociological perspective, and I expected that this will be will get more sophisticated once I interact more with scientists and engineers at NTU to develop this model. Yeah. Okay.
No other questions? These will be our next speaker, Modeling and Simulation of Human Complexity.
Okay. So yeah, today has been very exciting for me because all the talks have been very, very much in my research area. So I've enjoyed it very, very much. What I've decided to do is give an overview of what's happening, the research that I'm taking part in the School of Computer Engineering at NTU. And this is primarily on agent-based modeling, so a lot of what we heard about this morning. And what I mean by modeling and simulation of human complex systems is that the agent-based systems I'm interested in are generally representing humans and human behavior. So my background is I did a degree in AI. I'm a computer scientist, so I have interest in human behavior, but I'm in no way a psychologist. The things I've been focusing on recently are crowd simulation, that's along with other colleagues in NTU, and most recently on traffic simulation, particularly with electric vehicles in Singapore. Then I have a slide at the end, which I think we've actually covered quite extensively this morning, but that's two of the challenges and questions that I'm always faced with when I'm describing the kind of simulations I'm doing, and hopefully we can, I can get some experts' help in how to answer these questions. So for the crowd simulation that we've been doing, it's quite different to the things that Dirk Helbing has been doing, which is the social force model. The philosophy that we adopted was that we would build heavyweight agents, with each agent having kind of a cognitive architecture. And these architectures are ones that we'd adapt from the cognitive science literature. So our agents are computationally complex, completely the opposite of what Robert Axel had done. But this was generally because we wanted a naturalistic approach. So we want our agents to make the same mistakes that humans make. We want them to have the same limitations of perception. When they're trying to escape from a burning building, that they'll make mistakes and they'll make misjudgments. So we try and build that into our models explicitly. So some of the examples of the things that we've done and the cognitive theories that we've applied. Gary Klein's recognition prime decision making is one that we've used fairly extensively. And this is quite similar to the BDI architecture that you have in AI and agents there. Social schema theory, we've looked at how groups form during evacuation and how parents will look for children and how this can have a great impact on the actual consequence of an emergency. And also, recently, we've looked at Scherer's appraisal theory to try and describe how emotion happens within a crowd and how emotion can spread throughout the crowd. So I'll quickly go through two examples of how we've applied the crowd simulation. One is we've used it for training. So we've worked with MINDEF in Singapore. And this is where we've used our model of emotional contagion. And we've interfaced our crowd simulation with a serious game that the military used to train their soldiers. So we have a virtual crowd which can react to the soldiers' behavior, and you can have instigators within the crowd to try and spread this emotion and try and make people angry. So you look at various strategies about where you place soldiers, how they patrol, and how they interact with the crowd. So we've done some preliminary experiments with this to see, again, when you're doing this kind of translational work, you're taking cognitive theory and applying it into a simulation, you start to see the holes. You start to see that qualitative kind of models don't always have the basis that they should. Secondly, something else that we're doing at the moment, this is a nice application of complex systems, I think. So we have a system which we call a symbiotic simulation, something that's interacting with the real system in real time. So you have a building with some sensors, which is reporting where fire is, reporting where people are through CCTV, where smoke is spreading. And at real time, this is feeding into a simulation which is trying to analyze an optimal route for the evacuees to take. And then you have interactive signboards within the building to try and direct people out. And you have this changing in real time as things are happening. You have congestion at certain doorways, you have fire spreading in certain directions. And the things that we're interested in there is how trust. So if you have a system which is directing people out to a particular exit, and that starts to change very frequently, people soon lose trust in the system. So we're trying to dream up clever ways of trying to measure this trust and trying to understand exactly how trust will change with such systems. And also robust simulation. So when you're doing this symbiotic simulation in real time, it needs to be fast. And you need to deal with incomplete information. You may not have perfect information. So how you can account for that with repetition and with certain statistical tests. So now onto something a bit different. This is something that I'm doing with an NRF project with the University of Munich. And they're planning to develop an electric vehicle in Singapore. So what we have is taking some of the ideas that we've taken from crowd simulation and applying this to traffic simulation as well. So some of the things I'm interested in, this is very early work, but the other scientists are deciding on particular designs for the vehicle, how large the battery needs to be, how the air conditioning is going to be powered. And I'm trying to look at how these things interact. So if you have a very, very short life battery and you have traffic jams in Singapore, which you do, and you're sat in a traffic jam with your air conditioning on, that's going to draw a lot of power. And as soon as you start to see a few cars break down, then you start to see a consequence in the entire system. You see a quick collapse of all the cars and everybody's stuck. So trying to understand how charging behavior and how the number of cars on the system will affect this is something that I'm interested in. And we have some other people who are designing very, very sophisticated computing systems which can give real-time routing information. And if you get this routing information, how does this affect the system as a whole? If you get up-to-date information about the PIE being very, very jammed and everyone shifts to the AYE and then back to the PIE, can you get kind of oscillations in the system? So this is my last slide. And all the kind of problems that we're dealing with are quite applied. They can be applied in decision support. And whenever I give a talk about the kind of things that I'm doing, I'm always asked one question, which is about validation and how you deal with this. How do you get data on emotion? How do you get data on driver behavior? And obviously computation. So the center I'm in is the Parallel and Distributed Computing Center, and the scalability issue is something that I did for my PhD. So there I think we have more answers. But for the validation, then data is obviously important. And my kind of suggestion would be that this is really the kind of thing that will be helping agent-based simulation in the future. So, for example, we have one person who's developed an app for the iPhone which can detect acceleration behavior. So if you take the classic acceleration models, cellular automata models of drivers, you can actually get real data of drivers by using the phone. It's very easy to get the acceleration profile of a driver. And if you've ever been in a Singaporean taxi, you'll know that this is quite different in Singapore. And in electric vehicles, this is good because you have regenerative braking. So the harder you brake, the more energy you can recoup. But really, we've done a few ways of trying to use crowdsourcing as a way to get behavioral data at the micro level, at the individual level. And I really think the coupling of this technology with agent-based modeling is what I see as the future. So, yeah, that I will stop.
More and more time for questions. So,
yeah. So you take things actually a couple of steps further than just trying to understand the complex system. You also want to control it. Like you said in the example of, for instance, the evacuation thing, where you want to adaptively change what's happening there.
Yeah.
Okay, so then the issue of psychology comes in directly with all the examples that you were giving.
Yeah.
And you mentioned this thing like trust.
Yeah.
Do you have any idea how to investigate that? Any idea how to quantify trust?
Well, there's another field of computing called human computation. And this is a way that you can get humans to do computation for you by making it fun. So making it a game. So we have developed this game that we're about to release, which is a maze game, and the player has to navigate through the maze And they can use a navigation system which they're told something about, that it's always going to be honest to what it thinks it's going to be, but it may make mistakes because it doesn't have complete information. So the users can then start to follow the system or not follow the system. And they can score various penalties or various scores for different things. Then what we do is we change the system so that it will oscillate. So it will say go right, and then it will say go left. And what we're trying to understand is the frequency of this change and the magnitude of this change, how it will affect people's liability to follow the system. So I think you could do a real-world experiment to the same effect. You could put people in a room, you can do the same thing. And that's what, if I had the funds, I would love to do. But the cheap way to do it is with these kind of techniques.
Then you might be aware of a study that they did exactly on this thing, where as soon as they kind of switched from, let's say, from like a traffic light for, okay, this is red, you should not go here, and this is green, yes, you should go here, that will frustrate people constantly if you switch that. And that will actually frustrate the whole system. But what they did is they had a range of colors. So, you know, it's a bit greenish, so this might be the one that did. And if it changes there, if it changes from a bit greenish to a bit more red, people feel much more comfortable than just if it switches like that. So this very subtle thing, it's really subtle like that.
Yeah, there was a big study I've read recently by the European Air Safety Board, and they've done similar studies and trying to understand trust in computational systems. So they have the air traffic management systems which are semi-automated. So in some ways, if the air traffic controller is trusting this, it can make things worse because they can become over-reliant on the system, and that can actually make things far worse. So I don't think it's an easy thing to do, but I think it's important and interesting. So.
Okay.
Yes.
We've already come to our last speaker. This is Justin Dowell. He's the only one here in the except for Monique that I can address in Dutch, but I won't. And he will talk about abnormal complex patterns in the brain and how to detect them.
Good evening, my name is Justin Dowels. I'm from the School of Electrical and Electronic Engineering. And my background is in machine learning, signal processing, and information engineering in general. Now, over the last 5 years, I've tried to use my own expertise in the area of neurology. So I'm working closely with neurologists, trying to develop tools for diagnosis and treatment of brain disorders. Now, so what does it have to do with complexity, you may ask, right? And I think, well, obviously the brain is very complex. It's a very complex organism. You can think of it as a network with many different components, neurons. And so I think when you deal with brain signals, there are at least 4 key questions. Yeah? For example, how can we quantify the complexity of signals? Yeah? That's important in the context of diagnosing Alzheimer's disease, for example. Second question, how do we make sense out of complex signals? For example, surgeons, they measure brain signals and they have to make a decision. Should we operate this patient? So they have very clear decisions to make, and the information is very complex. Yeah? Third question, how can we represent complex signals? And at last, how can we model complex patterns in signals? So these are kind of 4 questions I'm dealing with from the viewpoint of complexity. Now, I will briefly highlight each of them. So my interest again is in using signal processing to help decision making in clinical context, in particular in neurology. And so as a first step, we measure brain signals, for example, electroencephalograms using electrodes on the scalp. Yeah? And then we extract features from the signals. And then as a last step, we combine the features and make a decision. It's a bit like you're trying to solve a crime and you collect evidence, and based on that you make your decision. So of course the goal is to have more reliable diagnosis and treatment. Yeah. Let me show a first example. It's about diagnosing Alzheimer's disease using EEG. So why EEG? Well, EEG is a simple technology, it's mobile, it's inexpensive. Now it turns out that brain signals in Alzheimer's patients are less complex. I think it's a very interesting observation. Also, they're less synchronous, and they show slowing. The signals become slower, and so for us, it's quite important to be able to quantify complexity, because it helps us to diagnose Alzheimer's disease. Yeah, so you can think of the brain as a system, of course, and it turns out it becomes less complex in particular brain disorders. So that's one way I am confronted with complexity. So we compute different measures of complexity, for example, entropy, and that allows us to diagnose Alzheimer's. I can give you here some figures. Up to maybe 80 to 87%, we can classify or separate, distinguish Alzheimer's patients from healthy people using electrical brain signals. A second project I'm involved in is about trying to localize the seizure focus, which is the brain area that causes or triggers epileptic seizures. So of course it's very important to know where that is, because surgeons may remove that brain area, so you have to be very sure about it. You cannot just remove it and plug it back in your brain. So it's a very risky decision, yeah? Very strong risks. Now, let me point out the key issue. The key issue that we record from the brain, yeah, we have lots of brain signals. The signals are very noisy, yeah? You have complex patterns, and eventually you have to make a decision, a simple decision. Should we do a surgery, and where, yeah? So we're dealing with, so surgeons have to deal with this every single day. And so that's what we're trying to do is complex decision making in this context. We're computing different measures, statistics of the EEG signals. We develop complex decision making tools, and then eventually we make our guesses about what area is causing trouble. So here the question is how to make sense out of complex data. Third topic is about how can we intuitively represent complex data. Yeah? Here it's about transforming brainwaves into virtual reality, in particular graphics, sound, and haptics. So this is joint work with people from IMI and many students who work on this. So the idea is, the concept is to create a space where it's like you're standing in your own brain. You can sense your own brainwaves in real time. That's actually what we're doing. Yeah. So we can see, hear, and touch your brainwaves. So, and of course, you're dealing with complex signals. We're trying to make them as simple as possible, very intuitive. And here you can actually control the output using gestures. You can talk to the system. It can change adaptively to your own preferences. It works in real time. I can show you a video. Oops, oh, I'm sorry. Here. So it's a bit dark in the room. It's in the immersive room. There's one person that is recording brainwaves, and here we try to grow a forest, yeah, from the brainwaves. I'm living on campus, NTU campus. I'm living in the forest. That's how I got my inspiration. So you see, the more active the brain, the more, or the more the forest is flourishing. Actually, we also have sound. You can hear birds, animals. So we've run this at IMI. We have had many visitors. We're also going to show this at the Science Center in Singapore. The next 5 years, we will have a demo, so people can try. And if you have time, you can check it out. So this is an example of how to visualize, how to represent in an intuitive way complex signals. Yeah, so that you can understand it, or you can get some affection with it. At last, modeling of complex patterns. I'm very interested in understanding how epileptic seizures start, evolve, and end. Now, usually if you think of the brain, of course, it's a very complex system. However, during seizures, the signals are very simple, well, relatively speaking, yeah? So you have clear oscillations, bursts, I cannot use a mouse, and they're all nicely synchronized. That's amazing. So this is the ending of a seizure, the termination of a seizure. So you have clear bumps or bursts, tuck, 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 and all of a sudden, they all disappear at the same time everywhere. I think that's a clear, nice example of a complex behavior or of emerging behavior. So my question is, can we use tools from complexity to understand this behavior? That's very important, not just for pure science, but also for helping epileptic patients. Because if you know what's the main mechanism behind this, we can develop, for example, perhaps new drugs, perhaps new neural implants to prevent seizures from happening. Okay? So that's my 10-minute talk. Just let me summarize. I'm looking at complexity from 4 different angles. I try to quantify complexity, I try to make sense out of complexity, I try to represent complex signals, and I'm trying to model complex patterns and signals. Thank you very much.
Thank you. Now, it's collected 3 minutes this afternoon. Okay, 5 minutes work, 5 minutes questions. Questions to Justin?
So,
Dutch, yeah.
That's
You can do it in Dutch.
Conspiracy.
no, that's not good. So, there is this nice work on Parkinson's disease.
Alzheimer's.
No.
Sorry, I'm talking.
This is the introduction to my question.
Sorry.
This is nice work on Parkinson's disease, where these kind of unexpected tremors come up.
Yes.
And people control that. They have now found a way to control
Yes.
that by an implant where they put a certain frequency,
Yes.
small electric
Exactly.
pulses, and then suddenly
Yes.
there's a complete relaxation of the patient.
Mhm.
It's absolutely amazing.
Yes.
I saw it working within a patient in Germany a couple months ago. Is that comparable? Is that the kind of thing you're looking for?
Yes, but then for seizures.
Yeah. But
So
could you use their technology because you're looking for ways to quantify and but you said complexity tools to actually quantify.
Yeah, first of all, we'd
could you
like
use their tools for that? Because they have whole feedback system, right? They measure this onset of tremors in terms of the EEG signals. Then they have a simulation actually that says, I have to act. That sends a pulse to the electrode in the brain,
Yes.
and that then relaxes the patient.
Exactly, so that's very useful, that's very similar to what you're doing. I think people from complexity science can contribute to that very well, because I don't think there's a deep understanding of what's going on. I think there is some, how can I say, I think there are more generic principles behind that, and people, typically in neuroscience, they will model particular ion channels, particular neurons. I think they're missing kind of the overall picture. So maybe there is a connection between Parkinson's and, say, epilepsy, maybe autism.
Yeah.
And maybe there is a way, by using complex systems tools, we can unify all that and we can have a higher or deeper understanding of what's going on. That may lead to better and more interesting devices and also drugs and different therapies. That's my motivation. So I would like to develop generic models and then translate them in biophysics. So if you talk about network connections, what do you mean? Are you talking about anatomical connections, synapses, or maybe chemicals that are communicating with each other? So we try to go from the mathematical world to the biophysical world. I mean, that would be step number 2. Step 1 is to build a complex model using tools that I've learned today, or at least heard about today. The second step would be to translate the mathematical world, with the mathematical description, into a biophysical description. And then you know exactly the variables. Maybe is this chemical? Then we can think about designing drugs. You see? So that's how we think about this.
Yeah,
Very small, very short.
So I was pretty much impressed by the 80% recovery you had with Alzheimer's.
Not recovery, it's diagnosis.
Yeah, I mean,
Yes.
that you were able to actually identify that it was Alzheimer's.
It's very early stage.
Do you have many false positives in there?
No, I wouldn't say so. But 80% is overall, yeah.
Mm.
So I guess about 20%. I'm not.
But then it doesn't know. The question is.
I don't know. I
Okay.
don't know the exact numbers, to be honest with you.
Okay.
I would say it's not yet ready for prime time. Yeah, I mean this is still under development. We have results for a few data sets, it is not differential, so we can distinguish Alzheimer's from healthy. But how about Alzheimer's or different stages of Alzheimer's, or Alzheimer's versus dementia or autism? That's much more difficult. So we kind of doing a simplified problem. We're dealing with a simplified problem where we have Alzheimer's versus healthy, but there are many other questions, many other diseases that we would have to differentiate. So this is just the first step. It's promising, but it's still far from clinical applications, I think.
Okay.
Okay.
Thank you very much. And it is to me to close this session, which is actually quite easy. I'd like to thank everybody for their contributions. So another round of applause, but now for everybody.